Okay, so we're going to prove this identity that for all positive integers n, the floor function of this sum of square roots is always equal to the floor function of root 9n plus 8. So instead of working directly with the floor function, we'll try and prove some inequalities to show that this sum of square roots expression is always sufficiently close to the square root of 9n plus 8 that they do indeed have the same value when we take the floor function of them, so they have the same integer part is what we're trying to show there. And if you explore this by looking at a few different values of n, or perhaps trying to sketch a graph of each of these as functions, the sum of square roots versus root 9n plus 8, you'll find that the sum of square roots always seems to be slightly bigger than root 9n plus 8. So this gives us a sensible starting point, a conjecture at least, that we could maybe take root 9n plus 8 as our lower bound and try and show that our sum of square roots, root n plus root n plus 1 plus root n plus 2, if we show that root 9n plus 8 is always less than or equal to this, then this would show that the floor function of this square root would be less than or equal to the floor function of the sum of square roots. But we still need to bound our sum of square roots from above, and we can't bound it from above by the same quantity because that simply wouldn't be true. So instead of looking at 9n plus 8, we'll look at 9n plus 9, the next integer after that, and we'll try and show this inequality that it's strictly less than the square root of 9n plus 9. So now let's just explore where this idea has come from by looking at the square root of different consecutive integers to see why this is actually going to be sufficient to say that the sum of square roots has the same integer part as root 9n plus 8. So if we look at some consecutive integers, let's say we've got 14, we take the square root of this, then the floor function, we get 3. Then we go to the next integer, 15, the square root of this, and the floor function, we get 3 again. But then once we hit a square number, say 16, we're going to increase from 3 up to 4. And then the next one after this, root 17, is going to be the same. It's going to be 4 still, when we take the square root and the floor function of that. So we can consider a few different cases now, if 9n plus 8 and 9n plus 9, if either of them are square numbers, for example. But if we start with the case where neither of them are a square number, so this would be like having 14 and 15. So let's just write down, if neither of them are square, then you can see the 9n plus 8 and 9n plus 9 are both sandwiched between two square numbers, like how 14 and 15 are sandwiched in between 9 and 16. So we know that when we take the floor function of the root of each of these, we're going to get the same value. So then this inequality is telling us that when we take the floor function of either side, we get the same value. So this is telling us the floor function of the sum of square roots has to be the same as the floor function of the square root of 9n plus 8. So it is sufficient in this case where neither 9n plus 8 or 9n plus 9 are a square number. So what if 9n plus 8 was a square number? So if 9n plus 8 happens to be a square, then we'd be in a case like with 16 and 17 here, where when you take the floor function of these, you would definitely still get the same value because 9n plus 9 is only one bigger than this square number. So it can't be the next biggest square number because they're just more spread out than that. You don't have consecutive square numbers like that. So in this case, then, the floor function of root 9n plus 9 would definitely still be the same as the floor function of root 9n plus 8. And again, this would say that this inequality is sufficient then to prove the statement we're trying to show there. So this works when 9n plus 8 is a square. And finally, what if 9n plus 9 was a square? So we need to think a little bit more carefully here, because if 9n plus 8 is one less than a square number, we take the floor function of that, we would get, for example, 3 here if we had 15, and then the floor function of the next integer would go up by 1, which looks like a problem, but if we show a strict inequality here, then we're not actually working with this sum of square roots being equal to that square number. It's going to be ever so slightly less, so that in this example with 16, our sum of square roots term, instead of being less than or equal to 16, it's strictly less than 16, so it could be 16 minus epsilon for some small value of epsilon, we can say. And when we take the floor function of this, we do still get 3, which would be the same as the floor function of root 15. So in the case where 9n plus 9 is a square number, if we can just show that the sum of square roots is strictly less than this, so it's ever so slightly less than that square number, then we know that when we take the floor function, it's going to have the same value as the floor function of 9n plus 8. So when we take 9n plus 8, the square root of this, the floor function, we get some value, and the floor function of root 9n plus 9 increases, but if we can bound it from above strictly by this, then we're saying we're slightly less than that, so the sum of square roots, when we take the floor function of this, it is actually going to be the same as the floor function of root 9n plus 8. So we're actually okay in all of these different cases. So this explains then, you can explore this a little bit more if you like, but this explains why we're going to go with this as our sufficient condition, which means from here on we can actually avoid using the floor function at all and just focus on proving each of these inequalities for all positive values of n. And now let's work towards simplifying these inequalities before we actually try to prove them. So the first thing we could do to simplify here is actually square each of these three expressions, and because everything's positive, this would be equivalent to saying that if this inequality is true, then this holds if and only if the same inequality is true where we've squared everything. So on the outside now we just have 9n plus 8 less than or equal to our sum of square roots term all squared, which we'll deal with expanding this in a sec. But then you can see we've managed to simplify the outer terms quite a lot because we've just got 9n plus 9 and 9n plus 8 there. So then when we expand the brackets and square all of these terms, let's see what we get. So first of all, just for each of the squared terms, we'll have an n plus 1 plus n plus 2 for each of the squared terms. And then we have all of our cross multiplications. We'll have two lots of, we've got root n times root n plus 1, so plus 2. And I'll factor this in, instead of root n times root n plus 1, we'll put root n times n plus 1 in brackets. And similarly for the other pairs of terms, we've got n and n plus 2, plus the square root of n plus 1 and n plus 2 for all of our cross multiplication terms there. And you can actually see here that our n plus 1 plus n plus 2 term simplifies to just give us 3n plus 3. So now this middle term's becoming quite unmanageable. So let's take away 3n plus 3 from all three of our quantities here in our inequalities. So this is all going to be true if and only if we subtract 3n plus 3, we get 6n plus 5 has got to be less than or equal to 2 times our sum of square roots, so root n times n plus 1 plus root n times n plus 2, and finally plus root n plus 1 times n plus 2, and then this just needs to be less than 9n plus 9, where we take away the 3n plus 3, we're going to get 6n plus 6. And we can also divide through by 2 here as well, so we want to show then that this is true if and only if 3n plus 5 over 2 is less than or equal to our sum of these new square root terms, root n times n plus 1 plus root n times n plus 2 plus root n plus 1 times n plus 2, and then this needs to be less than 3n plus 3. So we've managed to turn this into something which looks slightly more manageable, though there is still some work to do on bounding each of these three terms individually from above and below to show that this inequality is indeed true. So first let's look at this square root of n times n plus 1 term. So we want to bound this from above and below, and there's actually a neat trick we can use here for our upper and lower bounds so that we get a nice upper and lower bound that don't involve any square roots. So if we choose some suitable value of, let's say it's a, and have the square root of n plus a all squared, you can see this would just give us, for our lower bound, n plus a, which is more in this format like 3n plus 5 over 2 and 3n plus 3. And we can do the same sort of trick for our upper bound. We'll try and bound root n times n plus 1 by n plus b all squared, the square root of that, which gives us n plus b, which is going to be nice for combining all of our upper and lower bounds in the end. We'll do something similar for each of these square root terms afterwards. So first of all, let's just look for a suitable value of b, and actually just by inspection, if you expand each of these expressions, we expand n times n plus 1, this gives us n squared plus n, and we want this to be less than n plus b all squared. We want this to be less than n squared plus 2bn plus b squared. So you can see that a nice value of b that this would definitely be true for would just be b equals a half, because then we'd have n squared plus n is indeed less than n squared plus, you'd have 1 times n plus a half squared gives you a quarter. So this is where b equals a half. So this inequality is definitely true for b equals a half, so we'll stick with that and see if that's good enough for the rest of our calculations. And now let's look at finding a suitable value of a so that this inequality is true. So again, if we just expand here, we've got on the left-hand side, we want n squared plus 2an plus a squared. We want this to be less than or equal to n squared plus n. So here we can cancel out our n squareds, and if we collect all of our n terms onto the right-hand side, we've got n times 1 minus 2a needs to be greater than or equal to a squared. And if we divide through by this 1 minus 2a term, we're going to have n is greater than or equal to a squared over 1 minus 2a. And this 1 minus 2a term, because we know that this inequality wouldn't work if a was a half or bigger, so we actually know that this 1 minus 2a term is going to be positive, so this is fine. And actually we could try and choose a value of a now, so that a squared over 1 minus 2a is just equal to 1. Because we know from this problem we're working with positive integers, so actually n is always going to be greater than or equal to 1. So we know that n greater than or equal to 1 is always going to be true. So can we try and find the value of a so that a squared over 1 minus 2a is indeed equal to 1? Well, actually this is just a quadratic which we can solve for a. So I'll skip some of the steps here, but you'd get a equals negative 1 plus or minus the square root of 2. And for our lower bound, remember we're trying to get something like n plus a, and then when we add together our other two lower bounds, we want to get something maybe slightly bigger than 3n plus 5 over 2 to show that the sum of square roots term here is bounded from below by 3n plus 5 over 2. So we don't want to take the negative value of a here, because then this would give us a bound which would be too low. So if we take the positive one instead with the positive, so let's write this as root 2 minus 1, so this is about 0.414. So then this would give us a suitable value of a, and if we can bound each of these quantities by something similar from below and then add them all together, hopefully our lower bound will be good enough to say that the sum of these square root terms then is greater than or equal to 3n plus 5 over 2. And now before we get to the square root of n times n plus 2 term, you might have noticed that root n plus 1 times n plus 2 is actually the same expression as n times n plus 1, where we're just replacing n by n plus 1. So we can derive some upper and lower bounds from the result we've just used for n plus 1 times n plus 2 now. We can just do this using a substitution. So if we replace n by, let's say, m plus 1, just introducing a new letter, we know that this is true for all values of n, so let's substitute in m plus 1. So we've got m plus 1 plus root 2 minus 1 is less than or equal to root m plus 1 times m plus 2. And this is less than m plus 1 plus a half, so m plus 3 over 2. You can see here your plus 1 and minus 1s cancel with each other. So now we can just replace the letters, because this choice of m is completely arbitrary here. So we've got m plus root 2. Let's turn this back into n plus root 2 is always less than or equal to root n plus 1 times n plus 2. And this is always less than, it's now n plus 3 over 2, just switching the letter m back into a letter n. So we've got some upper and lower bounds now for our third term as well. So now all we need to do is find upper and lower bounds for root n times n plus 2, then we'll be ready to bring these together and hopefully show that the sum of square roots is indeed bounded from below and above by these two quantities. And again, we'll use the same sort of approach. You want to bound root n times n plus 2 from above and below by n plus d and n plus c, respectively. So we just need to find some suitable values of c and d which work so that we'll get the right bounds in the end, but also so that the inequality here is actually true. So to see which values of c and d we should be aiming for, let's actually add together all of our lower bounds here. So this would give us a lower bound then for the sum of these three terms, or the sum of our square roots. So adding them all together, you see we get our 3n. Then we've also got plus 2 lots of root 2 minus 1 plus c. So this is going to be less than or equal to our sum of square roots term. And then for our upper bound, this is going to be less than now. We'll get a slightly nicer expression here. We still get the 3n, then plus a half plus 3 over 2 gives us plus 2. And then we've also got plus d here. So now we need to try and find suitable values of c and d. So we want our lower bound to be at least 5 over 2. So we want this entire term here, 2 root 2 minus 1 plus c, needs to be greater than or equal to 5 over 2. So now if we rearrange this and solve, we get c needs to be greater than or equal to 7 over 2 minus 2 root 2. And this number turns out to be, it's around 0.76. But to actually make life easier for ourselves when we're proving this, we should have some flexibility. So let's actually try just c equals 0.7, and we'll see if that works. So we still need to show that this inequality is actually true with c equals 0.7. So we'll come to that in a sec, but we also need to find a suitable value of d. Actually here it's much easier. We're trying to find an upper bound of 3n plus 3, so let's just take d equals 1 and see if this works for our upper bound. So now getting on to actually proving this, let's substitute in c equals 0.7 and we'll see if this works. So we would need n plus 0.7 all squared, the square root of this. We want this to be less than or equal to the square root of n times n plus 2. And we know that this is going to be true if and only if, first of all, we can take square roots on both sides, then expand each bracket. So this is true if and only if n squared plus, we'll have 1.4n plus 0.49 is less than or equal to n squared plus 2n. You can see once again our n squared's cancelled, and if we collect all of our n terms onto the right hand side, we can see that this is going to be true if and only if 0.49 is less than or equal to 0.6 times n. Then this is true if and only if 0.49 divided by 0.6 is less than or equal to n. And here this we know is actually true because we're only really working with positive integer values of n. So we know that this is true because n is greater than or equal to 1. So this inequality, n plus c less than or equal to root n times n plus 2, is indeed true then with this value of c equals 0.7, which will be good enough when we add together our three lower bounds to show that 3n plus 5 over 2 is a lower bound for our sum of square roots term. So now we'll just clear some board space and we'll do the same for d, then we'll be able to bring together our three inequalities to finish proving the intended identity. And now to check that this upper bound does work with d equals 1, we just need to verify is the square root of n times n plus 2 definitely less than n plus 1, which we'll write as the square root of n plus 1 all squared. And we know that this inequality is going to be true if and only if the same inequality holds but where we square both sides. So we can also expand the brackets as well. So we get n squared plus 2n needs to be strictly less than, when we expand the brackets here, we get n squared plus 2n plus 1. So you can see this is definitely true because we've got the same expression plus 1 is going to be bigger than n squared plus 2n. So this upper bound does indeed work then with d equals 1. So now we can combine our three lower bounds and our three upper bounds to check that our sum of square roots term is indeed bounded between these two terms as we'd like. So for our lower bounds, let's just write out the sum here. So we have, adding these three lower bounds together, we get 3n plus, we'll have 2 root 2 minus 1 plus 0.7. We actually saw earlier, or you can verify if you like now, this is greater than 3n plus 5 over 2. So we've shown that our sum of square roots expression here is bounded from below by this term, which is itself bigger than 3n plus 5 over 2. So we definitely have this 3n plus 5 over 2 as our intended lower bound. And then if we look at the upper bound, this is even nicer because we've actually shown directly, if you add these three together with d equals 1, we've shown directly that our upper bound, the sum of square root terms, is strictly less than 3n plus a half plus 3 over 2 plus 1 gives us 3n plus 3. So we've got our lower bound and our upper bound for this sum of square roots term, and this is enough then to prove the original identity, because this shows that we saw this was sufficient for our original sum of square roots term root n plus 1 plus root n plus 2 to be bounded between root 9n plus 8 and root 9n plus 9, which then, as we saw at the beginning, was sufficient to say that the floor function of the square root of 9n plus 8 is actually going to be exactly the same as the floor function of our original sum of square roots expression, root n plus 1 plus root n plus 2. So then we've proven our original identity at last.